Hi everyone, can everyone hear me? Welcome back to this week's session. I hope everyone's doing fine. Uh, Clemens unfortunately could not make it today, so he asked me to fill in for him. If for those of you who don't know me, I'm Matthew Tam, and I'm also part of the Karamba team. And we'll be basically going through uh, continuing on from last week's session with the bridges that Clemens started with. Uh, if you have any questions or issues, you can feel free to write them in the chat, and I'll try to respond to these questions or queries immediately. First, we're going to start off by responding to some of these questions that some of you posed last week at the end of last week's session. If there are any issues, please write them in the chat there. Can everyone hear me okay? I'm assuming everything's all fine. So I will start soon. Give me one sec. Okay, yes, I got some messages that everything's working fine, so we will begin shortly. So, just one question. Someone asked if there's a version for the Mac. We are currently working on a Chrome version for Mac. It does take some time to develop, and we're hoping to have it ready in the next few months. So stay updated with our webpage and or our LinkedIn to see when this is released, and we'll definitely keep you informed. In relation to last week's webinar, someone asked, yes, this webinar is still available on our YouTube channel and also on our website. You can simply click on the link and you should be able to still follow it. If you have any issues, just feel free to write us. But the webinar should still be live on our YouTube page. Other than that, then maybe we will start with our session. I know that a lot of you are probably having some holidays, so thank you for joining us once again. And we'll begin. So, as you all remember, last week Clemens showed you how we made this one-dimensional bridge, this arch bridge. What I want to explain, because some people were asking actually, why in the model view we have set deformation to 0. Basically, what we are doing is taking the moment curves to generate the geometry of our arch. We can either leave the deformation turned on or off, it would have no difference, but if we were to activate the deformation, oops, sorry, I'm in the wrong. If we were to activate the deformation for our geometry generation, you will see that the actual section forces that are created, which is like this, are also deforming according to the original shape. And which means if we were to activate the deformation, you'll see that the geometry of the bridge actually deforms accordingly. So you would have some funny results. So you can even play around with this to see what sort of results you could get. But this is the reason why it's left to 0. You can turn it off and it would have the same effect there because its deformation is deactivated or set to 0. There was another question in relation to defining the members of the actual vertical members, these hanger members here that you see. In the line to beam component, we have defined these as 3 separate element IDs, the horizontal members, the arch members, and the hanger elements. And in the line to beam component, we're able to set if this beam or element has bending stiffness, therefore if it's a truss or not. As a default, it's always set to true. That means it does have bending stiffness. And if we set it to false, it basically acts as a truss element, and therefore does not have any bending moments. For those, someone just asked that they have the trial version to follow the webinar. If you have a trial version, then you might not be able to run the example. What you can do is reinstall Karamba to the free version. Otherwise, what you can do is also try and reduce the number of elements so that you only have a maximum of 20 elements. Of course, this might be problematic for you. You could try and uninstall Karamba and reinstall it as a free version of Karamba, and there you would have no limitation on the number of elements. There will be some components you see in the webinar that you will not be able to access with the free version. However, you will be able to still run the basic analysis and see the results on the truss with unlimited number of members in the free version. One other question that someone had was in relation to ULS and SLS design. So Karamba at the moment does not work with load combinations. We have load cases implemented, and you can define different load scenarios for each load case. You can also implement multiple loads in one load case. For example, in this case, we have gravity for load case 0 and load case 1. For the uniform line load, we have it only occurring in load case 0. And we have this also an additional line load, which is only acting in load case 1. In terms of the ULS consideration, what Clemens has done is applied a load multiplication. So in terms of 7.5 is referring to the width of the bridge, I believe. 0.5 because we have in reality 2 of these frames. So basically half of the load from the bridge is taken onto this frame. So he's multiplied by half. 6 is in relationship to the 6 kilonewton load. He has estimated, for example, build up and a load of 6. And then 1.4 is this sort of safety factor that he's allowed in this script. And of course, for different countries, you all have different norms. So you would have different SLS or ULS combinations, but this is the combination that Clemens has set at this stage for this definition. Okay, I think this was all for the questions from last week. Like I said before, if you have any other questions, feel free to bring them up and I'll try my best to answer them whenever I see them. So, as when Clemens finished off last week, we were already in the 2D version, the 3D version, where he started to basically duplicate this frame across and then apply these horizontal members to connect the bridge. And what this did was basically he did an analysis in the second order theory, and he also was doing an analysis in the buckling modes, because if you remember from last week, there was an issue with our buckling in the one-dimensional bridge, where here we have a buckling load factor of 0.2, meaning that if I was to visualize the buckling factor, you'll see that as the bridge is not braced in this direction, it starts to buckle on this axis. One clue for those of you who did not notice in Grasshopper and Karamba, if you do Control M, or if you use display mesh edges, you can actually see the mesh edges of our Karamba cross sections. So after applying this theory, we reduce the buckling modes to 1.7, the load factor, and we can also visualize this, the buckling mode there. So still in a similar axis, and basically in the next script we'll look at bracing this structure additionally. Just to go back to the PDF that we have, Clemens went to the bridge itself and was checking the way that the vertical members or the hangers are basically connected to the arch and the horizontal members of the bridge, and basically he discovered that actually these are not actually truss elements but actually stiff elements, so we have actually set them back to standard beam elements in our definition. And so you see here, Clemens has, rather than setting the hanger to a truss element by changing it to false, he has set it back to true because they are actually welded together. There was a question in terms of the logic of setting degrees of freedoms and supports and joints. I think in this example we haven't worked with joints, but you can look at the supports basically. When we are looking at the support conditions, we are able to support each point in a translation axis, X, Y, and Z, or on a rotational axis, so we can fix them basically. By checking this tick box, you can basically activate that this support position is locked in this axis. So for example, when I click or check or uncheck, you will start to see that you start to see these circles and arrows, these green arrows appearing. And these define support conditions of our bridge. In this case, we have fixed connections at the bottom of our bridge, and we have translational supports at the top of our bridge, basically in the Y direction. So these cannot move freely in the Y direction. And so we can define the support conditions. Often when doing bridge design, you might want to allow for expansion in the bridge, so that you might also even free the supports in one side of the bridge in the X direction too, so that you are able to allow for expansion or contraction of the entire structure too. So I'm going to now bring up the there was one question about the support flattened. For those of you who are not so experienced Grasshopper users, you might know a bit about tree structures and the way that data is organized in Grasshopper. The reason why we have to flatten the input, for example, we've also flattened the elements and we flattened the supports. If we do not flatten these, Karamba will keep the list structure of Grasshopper, which means that we keep the original tree structure. We have five branches here, which means that we would have actually 5 models. If I was to just disconnect this, you'll see that I have now 5 separate models for each branch. So this is important why we have to flatten the data in the assemble model component. so that all the data is fed into one model here. So as a general good rule of thumb, you should flatten any input into the assemble model component, unless in a rare case you are really trying to analyze multiple structures at the same time. But most of the time you'll be analyzing just a single structure there. So as you see, we have a buckling load factor of 1.7 here, which means that if we multiply the load that's currently applied by 1.7, the bridge will start to buckle. So the higher the buckling load factor, the stiffer the structure in a sense. And so going back to the PDF that we have, we start to also see that there are diagonal bracing elements in a bridge to brace the whole entire structure horizontally. And so for the next definition, we have started to implement these into our definition. And this is the fourth definition called Zollamtsbridge number 3. I just saw there's another question about changing the script of the hangers are replaced by tension cables. So at the moment, if I go back to the script, at the moment, Karamba cannot set tension only elements, but what you can sort of analyze is to check if these members are actually running in tension or compression. And we can basically use the normal forces. We can check the normal forces in each of these elements to see if these elements are running in compression or tension. There's also a component in Karamba called, in the full version, it's called, tension compression eliminator. So as I said, we cannot define that this element, one element will only act in tension or act only in compression, but we're basically able to eliminate elements which are acting in compression or eliminate elements which are acting in tension. So this is one workaround in a way to define elements only working in tension. So with this bridge now, you'll see that Clemens has now started to add these diagonal members, these diagonal bracing members here to stiffen the structure horizontally. In terms of how he did it was a simple extracting the points from these curves and then drawing the diagonal elements there, basically, like this. What we have defined, what Clemens has added is this as an additional line in the line to beam component as an additional element, and define these as only truss elements, that they do not take any bending moments. Sorry, I was just here you will see the cross sections that we have defined, and for the diagonal elements, Clemens has defined a cross section for these diagonal rods as a diameter of 2 centimeters with a thickness of 1 centimeter. So basically they're solid rods here. And so once we look at the buckling modes, we will see that with these additional elements, these additional bracing elements, we have a much stiffer structure, even though they are very, very slender elements. So we have a 9.6 compared to 1.7 as what we had before. We can check now also the buckling modes to see what the buckling shapes are, and you'll see that we have a lot more stiffer structure where we have the diagonal bracing elements. There. In terms of the load cases, we've kept everything to the same load scenarios. This last load is basically setting. Sorry, I have to place my analyze back to the model view so that I can visualize the second load case, where we basically apply asymmetric loads onto the bridge to see how it behaves. Maybe if I turn on my deformation, then you'll also see it a bit clearer to see how it behaves under different loading conditions here. And as this is a parametric script, we are able to go back from the very, very beginning where we generated the bridge. And here you'll see basically this entire bridge structure is generated simply for these two parameters at the start. This 5 and this 5 plus 7.5, which is the width there. And so with this, we can easily change the dimensions of our bridge, for example, or the position, sorry, here. The dimension of a bridge, for example, the width. And here we can control the length of a bridge. What we can also control is the relative position of the foot deck, of the bridge deck, sorry, to the arch. So we can move this, and then you can also see how the bridge reacts to this. At some points, as it is set parametrically, you'll notice that some of the elements disappear because of just the way that the script is written, that you might have some errors in the script. So be careful when you're editing all these values. And we can also change the division between each of the hangers, for example, here too, which might also have an effect on the diagonal members, as you see, because of the way that the script is set up. Some of the elements are manually sort of inputted, which are these diagonal elements there. So basically with this example, we have basically built up this whole bridge. I'm going to go back to the PDF to just show you some additional things that Clemens wanted to consider, but basically these were not then implemented into the model. For example, the railing could be used as additional structure. And there is another bridge that we want to go through, which I'm not sure if we'll have time to go through today, is this Truss Bridge, which Clemens will probably show you next week, along with some basic truss principles on why this sort of type of truss is effective for the structure. So I'm going to go back to my, what I wanted to explain is Clemens actually set up a script to explain how an arch behaves under different loading conditions. And what this means is that, so we have an arch which has been optimized basically for one load scenario, which is gravity in this case. We have this line. We applied the same principle to generate the arch from our bending moments, the bending curve, which is here. And basically, gravity is the load that's governing this arch form. And what happens when we then start to apply different load scenarios onto this arch? How does this arch behave? And so with the similar definition to what Clemens did last time is we have this arch which has been scaled and flipped from our original bending curves. And with this, we're dividing the arch into separate segments so that we can apply point loads along the point of the arch and see how this arch is behaving. So we've basically then taken the endpoints of the arch, assigned supports, so they're basically fixed supports, and then we have some different free load scenarios where we want to check how this arch is behaving and check if the principles of the arch behavior are correct. In the first case, we're looking at simply applying a simple point load at a position on the arch. This position can be controlled by this slider here. And as you see, as I move the slider from 0 to 1, this point load moves along the arch. And you start to see the bending forces inside the arch. And what you see when we're at 0.5, which is the center of our arch, you see that we have a very symmetric system. And then at approximately 0.25, we have the highest bending force in our arch. And what Clemens has done is to use a simple optimization to check where we have the highest, basically where is the weakest in our structure, the highest bending force, basically taking the elastic energy of our structure and optimizing the maximum result of this elastic energy for this load case. So if I double click on our Galapagos, I'm making sure that I click maximize because I'm trying to find the worst solution in a way where I have the highest elastic energy. And then if I start the solver, for those of you who are not so familiar with Galapagos, here you can set the preview. As a default, it's going to show only the best solutions. So here you see that it has the best solutions so far. And if I click on the first preview, you can see all the different iterations that it's doing for the check. I'm just clicking on there. And basically you'll see it start to converge into sort of one point, which is this 0.5 position. After a few seconds, you see the results are already very, very similar. And you see the change of the position is not changing much. So basically, I can even take that, reinstate it, and if you check in your Grasshopper script here, oh sorry, I noticed that my Galapagos editor is not showing. Let me see if I can add this. Sorry about that. So for those of you who missed the Galapagos preview, I made sure that I set the fitness to optimize for maximum result. And then basically I can run this over, and I'll just run this over again. If I run it, you can see that it's basically optimizing for different positions. If I set it to display only the better genomes, you'll see that it's basically staying at the same value. After a while, it will converge, but I'm just going to stop it right now. And if you reinstate this value, you'll see that this is 0.5. And so this is a 0.5 or 0.75, which is basically a quarter or 3/4 of along the length of your arch, is giving you the worst possible result. So that is its weakest position along the arch. At the moment, you can also visualize the actual, if I zoom in, I can see the value of the moment at the specific point, which is approximately 21 kilonewton meters at this point. So this is looking at how the arch behaves under a point load. What happens if we set the load case to 1 and we have now a uniform line load? So in this case, we have a uniform line load of 10 kilonewtons per meter. We have this position of the point of the load basically distributing along approximately half of our structure, divided there. This is basically we haven't defined any beam IDs in this case. So what Clemens has done is actually applied the loads according to their element number. And so basically in Karamba, each element has a unique number or index in this case. And so here, I believe we have, we can check, we have 100 beams. So they starting from 0, each beam has a unique index from 0 to 99. So with this information in mind, basically I can create a list of numbers using the series component, which can define which elements are receiving this uniform line load. In this case, we've set the load case to load case 1 and load case 2, and we've applied it as a global projected load. So if you imagine, in the case of our bridge from before, you imagine that basically it's applying it as a vertical, as a straight horizontal load, where elements which are steeper in the decline receive less load, and elements which are lower which are not as steep receive more load. And this is the same case as how we have it in our bridge, because we applied the line load basically on the horizontal deck of our bridge. If we apply a global load, you'll see that the load distribution is slightly different. And if I was to apply the load then to the entire structure, you'll see that I have a lot higher bending moments in our structure too, as compared to our global projected. So here we have an evenly distributed line load across the entire arch, which is applied as a global projected, where we have sort of high moments at certain areas which vary, whereas with the global projected we have a higher threshold for our loads, for our moment forces. And similarly for this, we can also run this optimization to see where we have the worst result. So if I turn this on, I'm just going to activate my window again, so that you can see it. And we will be maximizing again, running the solver, and you'll see basically where it starts to give us a maximum load, which should be approximately 50% of the arch. Stop it and I reinstate, you'll see it's at 0.5, and there's where we have this scenario. And then with the last load case, we have on the opposite side, just inverted load line load to see how then this is reacting. So basically you can see the behavior of an arch under different load scenarios. So I think in terms of the actual session, I'll call it for now. There are a few questions that I wanted to address before we finish for today. One question was related to the load that one arch's input is a line load. Yes, we are able to identify area loads using plates. We will be looking at surfaces, for example, in some future webinars, but you can define basically loads according to a mesh load. And basically these meshes, or surfaces in a way, can be distributed according to beams with their element ID. So you can input a mesh, in this case maybe a floor plate. In our case for the bridge, we can say we have a mesh here where we have the bridge, and then the load from this mesh is then distributed on these horizontal members and maybe on the horizontal members too. So we can define this by using the element IDs. And similarly, you can define the vector, whether you want to generate the loads as point loads or line loads. In this case, as we're working with beams, it would make sense to generate them as line loads. And we can also we can orient the loads according to global, local to mesh, or global projected loads. And then there was one additional question about options of exporting and importing. Yes, this is actually something that we will be going through. As you would see on my screen, we have in Karamba the default exporter, which exports the model to basically robot and RFM or RSTAB. This is a DSTV file, which is an STP file format, which then can be imported from various softwares. There are third-party plugins such as Geometry Gym, which I have here, for example, where you can export into different programs such as Robot, SIA, Sophistic, Space Gas, Strand, for example. And we will be looking at these into a future stage and maybe also looking to collaborate with some of these developers. As you all know, McNeil is currently also developing this Rhino inside Revit. And I think in 2 weeks, we'll also be having a session on Rhino inside Revit and how Karamba can be used inside Revit, and then how you can work with the geometry live or natively inside Revit and run an analysis there. In terms of a program for the next few weeks, Clemens also wants to look at bracing structures for high-rise or like high-rise buildings, for example. And then we'll be looking a bit into also different workflows, like I said, with different programs, and also some small optimization programs, and hopefully featuring some small lectures or presentations from some guests or friends of ours. And there was another question in regards to concrete design. Yes, we can definitely look at this in the next few weeks. As you all know, there is actually a component to optimize the reinforcement in concrete. So we could even look into looking at this in a future stage. So, like I said, thank you once again for joining us. If there are any other questions, feel free to write us, comment on our YouTube channel, or write us on LinkedIn. We'll try to keep you updated with any sort of developments in Karamba. and also with the webinar sessions. And thank you once again for joining, and we will hopefully see you again next week. Thank you. Bye-bye.